Oh, kia ora, folks. We are live. My name is Sam Kist. I work for Kind Order and I will be your MC today. Can we see slides? Oh, sorry, tipped my head a bit there. Today we're going to be talking through a whole bunch of projects and works that have been happening up in the Northland region, which is really cool. So to start with, I'm going to do an opening karakia. Feel free to join me silently if you like. Whaia te mataranga, kia marama, kia tupu, kia te aki ngā whenua, ngā moana, ngā arawai. Kia whaitaki ngā mahi katoa, araha atu, araha mai, tato ia tato, toi te tupu, toi te mana, toi te whenua, pomie, huie, taekie. Cool. This is our agenda for the day. We will start up with a bit of housekeeping and then we'll jump over to Greg from Toi Te Whenua, who will run through quick updates. And then after that, Anya, Duxfield and Richard Law from Northland Regional Council and Manaaki Whenua. And then following up at the end with WSP and Biophysical Regional Council. And we've got some speakers there too. The audience cameras and microphones are enabled. You can turn them on and off at any time. We encourage questions. If you want to write them down in the chat, please do. There's going to be a time after each segment for Q&A, so you can use the raise hand button there if you'd like to ask a spoken question. Also, the webinar is being recorded and will be shared afterwards. And we will have a list, I think, of the previous recordings on the Aotearoa Property Data Network website, which we can link to at some point during this meeting too. That's it for housekeeping. I will pass over to Greg Byrom, who's a senior geospatial specialist from Toi Te Whenua. Are you able to take up the screen sharing there?
I think I have done. Tell me if I haven't.
Take it away.
Brilliant. Kia ora, everybody. My name's Greg from Toi Te Whenua. Very brief LINZ update, LINZ news and updates today. Let me know if you can't see the graph. just making sure. Just an addressing update to begin with. So just to let you know that we've done 30,443 address edits from July to October, which is a reasonable number, as you can imagine. 8,252 for October is quite a good number, so that's pretty good for this month. There are now 2.3 million total addresses currently in NZ addresses, which is published on the LINZ data service. So that's good news from the addressing team. Just note that there's some updated guidance for TAs that are supplying address data to LINZ. So address updates can now be supplied as an ArcGIS REST service or as a WFS. So that's really good. That just means that you don't have to email us your address updates anymore. If you publish your data as a service, you can do it this way. Just a big shout out as well to a number of councils that are doing this already. That's Christchurch, Hurunui, Kaikoura, Napier, Palmerston North, Rangitikei, Taupo, Upper Hutt, and Western Bay of Plenty. So thanks to all those guys doing that. And also just confirming that LINZ's preferred address point location is centered on the main dwelling. So when you do that, that will be good. Thank you very much. For NZ suburbs and localities, there have been no major change requests received since June. There is one minor change request that has been processed. And you can see on the right there, it's one from Rotorua, so just a request to a boundary change there. And the next change request review panel meeting is in April next year. So looking forward to that. There's also an easier process now for updating suburban locality boundaries. And if you want to know more about that, you can email us addresses@linz.govt.nz for questions for any of these things, by the way. Addresses@linz.govt.nz. So you can find out about that. Just regarding historic property and sales data, we've had a bit of a push recently to get through all of the councils to get agreement to provide access to historic property and sales information. And thank you to all of the councils who've responded. That is everyone. And so all councils have now responded and given us access to this data. So thank you very much. One thing I do want to do, though, is call out one council in particular. And I wouldn't normally do this, but it's Christchurch City. Thank you to Christchurch City. The reason for calling them out in particular is because we didn't have an existing data sharing agreement with Christchurch. That's because their data was already open and freely available. So nevertheless, they have agreed to give us access to this historic data anyway without that agreement in place. So it's really good news. We've got all 67 councils on board, so many thanks for that. And regarding what we're doing with the Connected Property Data Program, we've published a property to building reference table, which is published on the LINZ data service now. So that's up there and ready to use, and you can find out buildings that are attached to your properties, which is good. The NZ buildings data set, which combines everything together into a customer-friendly form, is currently in the prototyping stage. Sort of looking at options for how we provide that data, and it's going to be used in particular to support the MB rapid building assessments in the event of a natural disaster, and also used for other things as well. So that's really good stuff, good news. It's going to be a big deal. We're also looking at publishing the untitled land work that we've been doing. Now, I realise this one has been in the pipeline for a little while, and it's actually been on the back burner a little bit because of the focus on the historic property and sales information. But we are going to be publishing untitled land on the LINZ data service very soon. So work is ongoing just to complete that and make it an available data set. So hopefully that will be done very quickly. And that's it from LINZ. If there's any questions, please send us an email, or you can drop them into the chat for me. Thanks.
Here, so our next presenter is Anya Duxfield and Richard Law, who both conveniently have their cameras on at the moment. They will be presenting on the land use layers created for Northland. So Northland Regional Council recently contracted Manaaki Whenua Landcare Research to produce land use data layers covering Aotearoa's northernmost region. And as a result, the council has much more information which will help them manage Northland's environment, the infrastructure, the economy, and quality of life. I will pass it over to Anya from there.
Thank you, Sam. My name is Anya Duxfield, and I am going to begin this, and I'm hopefully going to be followed by Richard. Can you see my slides?
Yep.
Awesome.
Nicely done.
Okay, so I'm going to be presenting on the data sets that were produced for us by Manaaki Whenua, and how we're putting them to use. I'd just like to thank the teams within Regional Council, the resource scientists, the economists who have helped me put this presentation together, because the majority of this is not my work, and I really only handle, or I'm a custodian of these layers rather than an honest to God user of them. What was the need for these new land use layers? The existing, what we used was the LCDB. It's national, it's at 1 to 50,000 scale, and it also hasn't been verified against the regional, the region's information. So we also had made a decision not to continue to use Agribase. We also wanted a high resolution data set that we could utilize with other high resolution modeling and mapping, for example, NIWA's clues. We needed something to support or enable analysis and decision making for freshwater accounting, economic impact, climate change, policy development, and land management mitigation measures. What were the objectives? Northern Regional Council asked Manaaki Whenua to produce a high-res spatial land use map, and it was to comprise of two parts: a primary land use layer to identify the major land use types at a primary parcel scale, and a technical layer that would include a wealth of information such as geology, rainfall, soil climates, and the sub-parcel land use classifications. Manaaki Whenua decided to use LINZ, which is the Australian Land Use Management Classification, for the land use classification. This is openly licensed, and the reason for using it was because there isn't anything that exists in New Zealand that we could put to this use. The decision was made to not use Class 2. It's because it's not relevant to Northern region. That's relatively natural production from relatively natural environments. It was adapted, but essentially minimal changes were made to the schema, to the classification. The start was to gather the data that would supply those land use for the Northern Regional. There's over 30 data sets that were used. They came from central government, they came from conservation groups, they came from the Land Resource Information System portal, they came from local authorities, and they also were directly supplied by NRC. Classification was achieved by basically combining all of that information using the LM schema. The land use spatial layers are useful in themselves. They're not just got the classification of land use. They've got a commodities list, management practice. They've got a land use descriptor. They've got a confidence score, and they've got a provenance, i.e. a source of where that data came from. And you can see in the background just a list of the data and the source and where it was acquired from. And this is basically the parcel land use layer for Northern Region. What did they supply? We have two spatial layers for direct use within the organisation. One is primary parcels, so it's by the at the parcel layer, and that was produced and that its companion is the aggregated cells, and those cells are something that Richard Law, if I leave him enough time, is going to talk to. They're based on the GGS, the Digital Global Grid System. So these are available in ArcGIS Enterprise for adding to any viewer, but also for anybody to use in ArcGIS Pro. We also made a decision not to offer up publicly the parcel land use layer, but we've offered up the aggregated cells, so that actually gives a much higher resolution description of how that land within parcels is being used. This is just a screen cap of the two side by side, showing that the parcel layer, it's it's the majority of the land use, but in the aggregated cell, you can see that it has a code which is grazing modified pastures, but you can see within that parcel that there is also conservation and land cover and water bodies. Then just down the bottom, you can see what is in the attributes that are available within each of those. So you get the LU code and a descriptor, and then any comments, source and attribution, and when it was actually acquired. Very briefly touching the digital global grid system, because it's the driver behind the second important part of this toolkit, which is the technical layer. So each of these, I think it's 300 million cells for Northern Region, has a set of information, geology, soil, climate, rainfall, and also the sub-parcel land use from the LM schema. So it's a three-tiered scheme, classification scheme. So at a very, very small scale, each of these cells has all of the information. So it's a very high resolution data set for these technical layers. I'm just going to very briefly touch on some use cases. These are some examples of how we've been using these three data sets in-house: freshwater farm plan property analysis, analysing water quality and land use within catchments, the climate change team to support their emission reduction targets, baseline state, informing policy, re-evaluating layers that we use throughout the organisation, erodible, highly erodible land and erosion-prone land, and a land management focus on surface water catchments, and we're going to rank them by impact, and we'll use the land use layer to help us rank where we should be actually focusing funding and mitigation attempts. This is the first use case. This is a freshwater farm plan property analysis. For this one, we use the primary parcel land use layer. We did a union between that and the district ratepayers database. So this is joined to the assessment number to sort of attempt to discover how properties were being used, what size they were, and this is just a brief capture of number of properties and what they are being used. As you can see, that we're sort of, the large properties are grazing and modified pastures, and then we've got a cluster in the middle which tends to be things like grapes and horticulture and famous keri oranges. Again, counting properties rather than doing acreage yet, but just breaking it down by the land use descriptors, just to get a feel for what's going on in Northland. This is just an example. We did it for horticulture, grazing, modified pastures, and for cropping at 5 hectares and greater than 20 hectares. This is the horticulture and flowers, vines, and market gardens. And this is just breaking it down by the LM schema, just to see property size, property count, and basically how we're using the land in Northland for these purposes. This part of it is on hold at the moment. Another use case is the water quality and land use summaries for all our catchments. For this one, we're using the aggregated cells because more useful when we were dealing with the freshwater catchments. So analysis of was simplified so that we could actually see, exotic cover, native cover, pasture that was non-dairy and dairy, and the breakdown for each of those catchments, and tie it to the water quality. The last use case is using the technical layers as well. Avanesh Govinad, who's no longer with us, he's an economist. He created an R script to create some spatial layers from the technical layers to analyze erosion-prone lands that fell in the LUC 7E classes, and find out how that land was being used. This was the driver for this was the climate change team looking at, maybe we should be moving land from pasture to forest. This is putting the technical layer, which are the cells, on top of the aggregated land use, just to have a sort of give you a good feel for what is involved here. I've clicked on one of the cells that's in grazing. It's also got a code of 7E1, so it's highly erosion prone. As I said, there are over 300 million of these cells in the technical data set. It's sort of essential that you do this outside of GIS. As you know, spatial joins will bring everything crashing down. This is just showing the LUC class 7E as polygons, and then just zooming in just to actually see that it is the technical layer that you've got. So you've got all the information there joined to land use. Same part of the study, but the script was then filtered for the slope that's contained in the technical layers. And you can see that this is over 35 degrees, and these again are being used by a climate change team. I clicked on one of these layers, and we can see that it's a modified grazing, so that the code's there, and that's the class, the LM classification, that land use that it falls into. Benefits. This was stolen from the final report from Manaaki Whenua. This land use spatial layers are a highly reproducible process. It's a consistent approach, so it can be used for land use changes through time. It has multiple attributes for each of the cells, and it includes provenance and confidence indicators. So very, very useful in analysis. It's high resolution, which is what we needed. Data sets don't have to be perfect or complete to be useful and added. Incorporates raster and vector without having to actually convert. And those are part of the technical layers. It uses the high resolution LiDAR and advanced tech layers alongside manually collected and point data. Again, reiterating that it has confidence indicators, so you can look at each of those cells and see how confident we are that that land use is actually what is happening in the field, or for real. Future plans, it's a core data set, so we need it for all our high resolution spatial modeling for our natural resource scientists, to basically be effective at resource management. It fills a hole, a knowledge gap that we have in our state of our environment. It helps prioritize for land management, what mitigation interventions should be and where they should be focused. It gives us a better understanding of how we're using our land and the intensity and the environmental impacts of that land use. And it enables us to actually do economic and social effects of the regulation that we're applying. These are just a few considerations about, from our perspective, now that we're actually using these for real. How do we go about ground truthing these land use layers? What should the frequency of these updates for the land use and the technical layers be? We need to grow our capability in the internal teams for GIS so that they can actually effectively use the land use layers. We need to grow our capability to use the technical layers. So growing our coding, our scripting capability in-house, and we actually need to grow our computing resource because they're complicated and huge data sets. We struggle, lack of CPU, GPU, and storage. And now I would like to hand over to Richard. Hopefully I've left him some time.
Have I got until 22, Sam? Is that right?
Yeah, you do. Leave a bit of space for questions and you'll be fine.
Okay, I'll do my best to fit it in.
Cool.
So quickly through it. So using a discrete global grid system for basically making reproducible land use maps with a whole lot of data. So what is a discrete global grid system? It's effectively a spatial data model. So rather than a format, like a data model, like vector or raster, that divides the Earth's surface into a system of hierarchical, addressable grid cells. It's discrete because each cell is unique and has an address, a stable address. They're global in the way that it offers a uniform global coverage. And it's a grid system in that the grid is constructed systematically. And if you have the knowledge of a grid cell address, you can construct its geometric boundary or identify its neighbors or its parent and child cells in the hierarchical structure. The example shown here is stolen from Uber's H3 system, but there are other DGGS systems that have different properties. So for instance, H3 is based on hexagons, which is nifty for doing things like modeling movement because there's only one kind of neighbor. But its downfall is that the cells aren't actually equal area. And also it doesn't have congruent nesting. So that red parent cell doesn't strictly spatially contain its child cells. It's only like a logical containment. Other grid systems exist, such as R-HEALPICs, which do have other properties like equal area cells that are maybe appropriate in different situations. So why is the DGGS useful? The main reason, in my opinion, is data integration. So the system of cells simplifies and discretizes data that comes from incoherent sources. So you saw about 30 plus sources we used in the Northland map. Some of those are vector, some of those are raster, but also just within vector data. So to associate multiple vector data sets, which have features produced at different scales and which are recorded with arbitrary geometric precision, which isn't really real. You know, the boundary of a forest and LCDB, you know, it's at a coarse scale, but the computer, as far as the computer is concerned, it's recorded with infinite precision. Well, not infinite, but very high precision. So it's defensible and actually computationally efficient to effectively ignore the precision at some level, to sort of pick an appropriate modeling resolution and beyond that level of detail to just, you know, not just assume, but know that the precision isn't actually there. So you can sort of do things at a known level of precision. The second reason it's useful is that it's a very well-suited data structure for efficient data storage and retrieval. So as a hierarchical grid system, data is effectively already sort of spatially partitioned by default. You can take, you know, a clump of cells identified by a parent cell offset at some level and treat that as a discrete unit. So those identifiers work as database indices, basically. And modern column-oriented data formats, if you've heard of Apache Parquet, for example, they're particularly well-suited to spatial data organized in a DGGS. And depending on the application, tools and formats can remain effectively unaware that the data is spatial at all because it just works on cell addresses rather than spatial objects. The third reason a DGGS is useful in this context is since it represents geographic space in discrete countable cells that are uniquely identified, addressable, and static, then you can effectively treat collections of cells or individual cells as elements in a wider set. So for instance, this means spatial relationships and spatial operations can be defined in terms of set theory. So take the typical GIS problem of computing the area of intersection between a collection of vector features. It's a very expensive thing to compute when you're working with geometric objects. However, the intersection of sets of integer cell IDs is not expensive to calculate at all. In fact, that's pretty much what computers are perfect at. So subtracting one set of cells from another, so taking one set of integers and another set of integers and computing the difference, can represent spatial differences, such as determining the cells in a forest area that are not protected by a particular conservation zone. You could easily identify if one spatial feature, that's a set of cells, is entirely within another. For example, checking if all cells of a habitat are protected. Relationships like adjacency are not as simple, but can be computed algorithmically. That's taking that systematic approach where you can take a cell and programmatically or algorithmically obtain its neighboring cell IDs, either immediately adjacent or at some distance away from itself. Yeah, so that's quite a useful thing. So for land use in particular, we could also think about land use models in terms of set theory. So if something, for instance, is covered in improved pasture, and the property also has an effluent consent, and we know that it has dairy cattle, then we can probably say that it's a dairy farm. And it's not any one of those things in particular that can tell you with high confidence that it is, because certain sources of data might be wrong or out of date. But the confluence of all of those things together can make you quite confident. And that's where those confidence scores come into this as well. If part of that same example property had a QE2 covenant, say, then that part of the property would not be considered a dairy farm in this hypothetical example, despite the presence of the other information that is indicating or attempting to indicate that it is a dairy farm. If you expand that idea to a full range of interesting classes like the ALM classification, and given enough input data, then you can begin to construct a general purpose land use map like we put together for Northland. This is just a graphical abstract. So we've published this idea recently in Big Earth Data. It's not quite impressed, but if you're interested in reading more and seeing our benchmarking experiments where we compared the performance of these ideas vis-a-vis raster and vector approaches, you can look out for that paper to be available to read soon. Here's an example of the maps that we've produced. So on the left, you've seen the Northland map already. And then on the right, we've got another example that was put together recently for a different project that uses an econometric model called NZ Farm that does basically land use forecasting under various assumptions about the future and the prices of commodities and so on. So both of these maps, you can see a class, but there's a lot more information behind them. So you saw the confidences and the dates and the scales and so on that go into ALM. And the one on the right, we haven't just got a categorical confidence. We've actually got a continuous probability variable and other various attributes, such as whether it's publicly owned land and so on, that are quite useful for modeling. That's pretty much it. This last slide for me is just some links to some tools. We've published 4 different open source tools that are available on GitHub, the Manaaki Whenua GitHub. The first 2, raster to DGGS and vector to DGGS, are just conversion tools. They currently only work with H3, but we do have plans to extend them to other DGGS systems. RHLPix DGGS Pi implements that DGGS that I mentioned earlier that has equal area cells, which is quite an important property. And RHP Pandas is a very new Python program that's available to use, which basically provides a more modern or familiar API for using RHLPix with Pandas data frames, if you're familiar with those in Python. And all of these are open source software, so feel free to use them and contribute to them and tell us how you get on with them. That's all I have to share.
Awesome. Thanks, Richard. I think we have one question in the chat, which was asking about, let me have a read, saying Ben thinks that a similar project had been done for Hawke's Bay Regional Council as well. Are there plans for other councils or are other councils interested in a similar approach as well?
Yeah, thanks, Ben. If I can try and segue this to an event that we're planning. So definitely many regional councils have this interest in land use information. Some of them do it in-house, some of them contract. Manaaki Whenua hasn't done work for Hawke's Bay, but I am talking to people at Hawke's Bay who are doing that work. We've done work for Horizons. And I'm actually putting together a seminar at the moment. If you're interested in the problem of coming up with a national land use classification like the ALIM one, but more specific to New Zealand, we want to put together effectively a working group or some kind of governance body where we can make collaborative decisions about what that classification should look like. But also wider than that, you know, what kind of practices should we have for land use mapping and what kind of validation steps should we perform, those kinds of questions. So I'm inviting particularly in-person participation for that in Wellington on December the 2nd, but if you can only attend online, I'll get a link out via Sam or something after this event that you can sign up for that event.
That'd be awesome. I'm sure there'll be folks here who'll be interested in participating and learning more about it. Any other questions for either Anya or Richard? Cool. In that case, we will proceed onwards. Our last presentation for today is on biophysical risk mapping, which is a joint project between WSP and Bay of Plenty Regional Council. We have Glenn Clarkin, Amy Dawson, Istvan Haju, and Glenn Trewick. Hopefully these four are on the call. So for this one, WSP's worked with Bay of Plenty Regional Council to develop inherent biophysical risk mapping for landowners for 2 different catchments. So using freely available data layers, biophysical risk maps were created for nitrogen, phosphorus, sediment, and E. coli, and validated in the field to create farm-scale outputs for the identification of risk. So this presentation will discuss the approaches taken and the outputs delivered. I'll pass over to, I think, Istvan to start off.
Yeah, thanks, Sam. I'm nervous about sharing my screen now, but I'll give it a go. So hopefully that goes through all right.
Yep, that's good. I can see that. Take it away.
Yeah, I think I'm going to pass it to Glenn Clarkin for a bit of an intro, and I'm happy to navigate the slides.
Cool. Thanks. It's fun. Yeah, maybe if you could just go to the intro slide. Excellent, thank you. Kia ora koutou. I'm Glenn Clarkin aho. I'm the Enterprise Systems Manager here at Bay of Plenty Regional Council. I'm actually filling in on this presentation for Pim DeMonchi, who's our Coastal Catchments Manager here. Unfortunately couldn't make it today. He's kind of the font of all knowledge in things land management, and so I'm coming at it from more of the GIS perspective, but I'll introduce the work that we did and then hand over to WSP. Yeah, so I guess this work started out of the need for helping landowners identify risk as part of the freshwater farm plans work. It actually started probably a couple of years ago, where internally our land management team approached our geospatial team, looking to understand where to prioritise their work for landowners for potential environmental plan work. So to develop some models and some map outputs to help them prioritise where to work. So the inputs to the initial models and maps were some of the things that actually Anya talked about previously, things like land use, slope class, soil type, rainfall, things like that. So that initial work was completed on I guess a sub-catchment, and subsequent to that, earlier this year, Pim and his team managed to get access to some extra funding through the Access to Experts program, and they approached WSP using our existing work to kind of refine and develop the models and outputs further. Yeah, so these are some of the fundamentals that were kind of part of what we wanted to achieve with the work, you know, reduce that cost to landowners, get an actual catchment view of risk, but still have that insight at farm level. Use our freely available data where appropriate, the stuff that we had access to ourselves or that was open. And one of the key things that we really wanted to do was make sure that the final product was open access, transparent, and you know, it could be reshared. So we really wanted to be able to share this with other regional councils, and that's kind of what WSP has done. They've provided our GIS team with a toolbox that we can share. There's still some fact sheets and some work on the methodology to come, but we'll start to be able to use that in-house, which is a great thing. Yeah, next slide, please, is fun. Yeah, so these are the major objectives of the project. So, like I said, consider those biophysical characteristics of the land to map the risks. So that's those things like slope and soil type, rainfall, etc. And it was really around identifying potential risks related to those things like nitrogen, phosphorus, E. coli, and sediment, and their impact on waterways. By understanding that risk, we could actually guide the choice of actions to avoid or mitigate those risks, and you know, our internal teams could help provide the right actions for on the land work, but also to be able to actually inform farmers or farm planners what was going on in their property. Pim's actually said it made it clear to me to make sure that you know, this is just an initial input into identifying risks. There are definitely other factors that go along with this. You know, good management practice needs to be considered. There are other layers that need to be considered potentially to get an overall picture, but it is a really good starting point for prioritising our work in a catchment. And yeah, like I mentioned before, that we wanted it spatial and to integrate several of these layers. So that is me. I will pass over to Istvan.
All right. Well, thanks, Glenn. And I'm actually going to pass it on to the other Glenn to talk about the details about the models and what it is doing and what it is not doing. Glenn.
Well, thanks, Istvan and Glenn. My experience in bringing to this project was I'm a soil scientist, and I've also been carrying out farm environment plans and auditing them for the last 10 years on Canterbury farms. So I'm aware of the interaction between risk and needing to develop risk profiles for farm environment plans. And it was quite clear that we were lacking something that brought the two things together easily for the farm environment plan process. So as was described, we're looking at the natural characteristics of the land that contributes to the contaminant loss to water bodies. So we're not considering farm management. So what the farmer does or how they do it is not considered in this. It's just what could potentially happen. We're not looking at any mitigations they may have applied. So therefore the maps that we've developed, they're not actually useful for regulation or limit setting, and they're definitely not perfect. So they're relying on the base data that we've used. Now, they're not useful for estimating contaminant loss or catchment load, and if a farmer has mitigated a risk, then areas that we've identified as high risk don't necessarily correlate with high output of contaminant. Next slide, please, Ishvan. So a farmer's diverse. Every farm's different, and they've got a different risk profile. There are different land characteristics, different management practices that we need to consider when preparing a farm environment plan. So typically what we would have to have done previously is consider each of these items in red separately. So we'd look at climate separately and try and determine risk, look at the soil type, try and determine risk, look at the land cover or terrain and try and identify the risk to those separately. So the maps that we've produced bring those factors together using the knowledge that we have in literature to try and determine what the risk might be from each of the 4 contaminants listed reaching a water body. So, like I said, we're not looking at these practices, the management risks. We're not looking at cultivation. We're not looking at stock management or nutrient use or irrigation or feed storage or any of that. But the maps can inform the farmer or the land manager on how they might carry out those activities or what mitigation practices they might apply. Next slide, please, Ishvan. So initially we worked in 2 catchments in the Bay of Plenty. Both of these feed estuaries and are considered quite sensitive. So they're reasonably scaled, 330 square kilometres and 103 square kilometres. So our assessment was to do some pilot studies in these 2 catchments, and then we've handed over to Bay of Plenty, who are working through the rest of the catchments. Ishvan, over to you.
Thanks, Glenn. So I'm just gonna talk you through the process, but maybe just a line about who I am. So I'm a geospatial specialist at WSP and part of the primary industries team. And I brought my geospatial expertise to this project idea. And the methodology is it's got a few steps, but obviously number 1 was to look around, do some research. What has happened in this space? What are the key data sets available to us? And what's the geographical coverage of those, etc., etc. So our focus area was Bay of Plenty in this case, but the tool can be applied in other catchments as well. So reviewed existing models. We know that there has been some efforts in this space, and they all different. They all have advantages and disadvantages. So we tried to take some of those learnings as well. And so the next step was to pick a tool to tackle this challenge. And I'm sure most of you would be familiar with some of the multi-criteria decision making techniques, and the analytical hierarchy process was our pick for the reasons that are listed there. So for 3 of the models, we used the AHP process. There are lots of reasons behind that. One of them is that the other Glenn mentioned earlier, that transparency and explainability that comes with this tool. So we can fully control what's happening, how we make the decisions. We can integrate this approach with GIS really well, and it has been used for decades. It's well established, well documented. So we thought this would be a good fit for this exercise, and it also allows bringing in the collaborative elements and expert opinion in a way that it's trackable, and we can make adjustments. We can run it iteratively. So that really helped us out, I think. For the other model, the sediment one, we used a more simple approach, which is a maximum value overlay process, because this one considers 3 different erosion processes, and it just seemed to be a more appropriate approach. Just a few words on the AHP process. So you start with building your hierarchy. So what your goal is. In this case, we wanted to identify risk. What are those different categories that we need to include? What are the geospatial layers that would provide that information? And then at the bottom level, you dive into the attributes and categories and alternatives. So you can consider these as a hierarchical structure. And then the next step in the middle, which is a pairwise comparison, we look at all of these factors and quantify the relative importance of those. So that takes us to the last step, where we we actually get to a point where we can calculate some weights and understand what layers play more significant roles than others. And then we can integrate this with GIS. So that's a very brief overview of what AHP can do. And in terms of the geospatial models, so the figure A summarizes the model for E. coli, nitrogen, and phosphorus. So we had the factors on the left. Obviously, there's a catchment that we would like to target, and then there's a series of geospatial processing steps involved, including transformations, rescaling, etc., and then eventually we end up with a list of rasters that we can run calculations on. And in this case, it is a sum of an additive approach. So we sum the factors, and we can make our risk index map. So we scaled everything between 1 and 5, 5 meaning high risk, 1 meaning low risk. In figure B, the sediment model takes into account 3 different factors, and then when we overlay them, we can run a function that will highlight the maximum of whatever value we have in those 3 layers. It will take the maximum, so that helps to focus on the most dominant process, if you like. So the next step was to sense check our maps, of course, and that was a joint effort. So we organized a field validation workshop and visited sites that were picked by the Northland Regional Council, and essentially took our maps to the field and checked whether they make sense or not with the eyes of experts and land managers and farmers involved. And we also ran a bit of a desktop verification exercise where we overlaid our maps on given locations and just pulled out the information that's feeding these models. So you can see that, like, point number 1 is considered sort of high risk. It's close to a waterway. It's got a valley bottom sort of geomorphology, and a given amount of annual rainfall. It's high producing grassland on poorly drained soil, so that is considered high risk in terms of E. coli, for example. And the green point indicates a low risk, so you can see the scores there. And obviously we had some learnings and we had to make adjustments. Some of our models needed a bit of tweaking, so they represent the reality better. And I'm just going to jump into a few maps for you. So the output looks like this when you look at a catchment. So that's for the Waihi estuary catchment. And on the left-hand side, you see the input layers. We also built in a couple of if functions. So it can take in fundamental soil layers and SMAP, depending on availability. Preference is SMAP and LIDAR data for the DEM, but it can work with other data sets as well. And when you zoom in at the property or farm scale, this is the sort of detail you can get with a bit of cartographic design. And then this is just to demonstrate the usefulness of these maps and the information. So just to check another at another zoom level. So we actually visited this site, and you can see how the reality looks like on that photo, and then how that looks like in the 3D GIS environment. And overlaying our maps highlight those areas along the waterway, and you can see that has been identified as risk before by the farmer. It's fenced off, it's planted. So this is sort of the outcome we want to achieve by using these maps to inform these decisions. And we were quite happy to see this alignment. So how can it work for you? It's an ArcGIS toolbox. So you need ArcGIS Pro. A bit of data processing is involved, and there is some other information that's needed. But it is all described in our methodology and manual document that will come with it, which is 99.9 99% ready to go. And essentially you just click run and it will run on your catchment. So just as an example, we implemented the models in other areas as well. So this is the Hauraki FMU, which is a much larger catchment. So the model works fine. And Glenn is actually from this area, and he confirmed that the maps make sense. And I'm gonna pass it back to Glenn for a second to talk about where we want to go from here. Thank you.
Right. So so I think we think we've got this to a stage now where it's looking pretty good, but we'd like to take it further and just tweak some of the aspects of it. We're looking for other potential funding sources or collaboration opportunities, or to see whether it will work in other catchments or regions. We welcome constructive feedback from anyone who's been down this pathway before, what they've found, what they haven't found. We'd like to develop a user interface to make it applicable or useful for different people, and work on different ways of visualizing it. Istvan's shown us a couple of ways, some 3D imagery and 2D imagery, and it'll be good to know how we can actually make this useful for a farm planning purpose. I think that covers it. It's just important to remember that this is just a risk-based assessment. So it's just a tool that will be used in the farm planning process, and it's in the years that I've been doing this, it is something that's lacking, and we would like to improve it and make it as good as it can, because it will really help the farm environment plans be fit for purpose and help people focus their attention and money on places that are going to bring the most bang for buck. So if you've got any questions or you want to get in touch with any of us around any of this, here's our emails here. So, and thanks to Bay of Plenty and Aotearoa for their contribution here.
Lovely. Thank you for your presentation. It was really cool. We'll open up the floor for questions, and I can see a red bubble in the chat. Ross Abercrombie has asked, how have Bay of Plenty Regional Council used this in a target catchment to tailor FEPs?
So I think, I don't know if you want to answer this, other Glenn, but we've only just completed the project, so it hasn't quite reached the stage of being able to be used yet.
Yeah, that's correct. Yeah, it's not quite at that level at the moment. The previous work we did, it's not quite at this level, but they used it to contact landowners basically to say, hey, we've got some funding, we would like to set up an environmental program, those sort of things, and that's likely what we'll do again with this work.
I had one question which was around, I guess the model will take some time to run. Do you have something at the top end that helps you pick which catchments you want to look at first? To help you prioritize where you're running the model?
I guess from regional council's perspective, the land management teams kind of know the catchments they want to focus on. Some of this is kind of understood, and so they'll probably prioritise it that way, I'm assuming.
Cool.
Yeah, I think water quality monitoring data tends to identify where there's a problem, and this mapping tool can help inform the risk for farmers when they're addressing those potential issues.
Cool. Right, we've still got a bit of time for questions if there's somebody else who would like to speak out or pop something in the chat. Otherwise, I will close this thing out. So first of all, thank you to our presenters, some of whose cameras are still on, but also thank you to Greg, Anya and Richard. Thank you for spending the time and coming along to listen to these events. We greatly appreciate it. The recording for today's session will be available online along with the transcript, and we'll share that out as well. If you are interested in the land use classification work that Richard is doing, the note for the invite is in the chat, but we'll try and send that out as well. The next webinar is planned for December, and it should be the final event for the year. And that one will be about New Zealand building prototypes, so watch out for that. And there should be a panel session and some presentation to look forward to there. If you have an interesting topic that you would like to share at the forum that you think other people should know about, please get in touch with us. We're always keen to share more of those stories out there so other people can learn from what you are doing as well. And to properly close this out, I'm going to share my screen and close out with a karakia. All right. Kua ea te kaupapa, ka rea nā hua, ka rere nā arawai, kua mau te mātaranga. Hei arahina nā mahi o tō tōtu te whenua. Kia tau te rangamari e, kia ranga i a tātou katoa, homi e, hui e, taiki e. Thank you all very much.
Thank you.
Thanks, Sam.
Good.
And thanks again, Richard.
Thanks, Anya. Thanks, everyone.
Nicely done. Seriously.